Morning, and just crossed the morning point, but welcome to the Communication and Signal Processing Seminar. We have a speaker today from France, and that's why we have a different time for this. So before I introduce him, though, I wanted to thank Kate Goodwin for helping organize the seminar series. It's been an invaluable help, and her service is greatly appreciated. So speaker today is Francis Bach. Francis Bach is at INRIA Paris, as well as École normale supérieure. He's a researcher at INRIA. He leads the machine learning team, which is part of the computer science department at École normale supérieure, and he's been doing that since 2011. He graduated from École Polytechnique in 1997 and completed his PhD in computer science at Berkeley, in 2005, working with Mike Jordan. He spent 2 years in the mathematical morphology group at École de Paris. And then he was part of the computer vision project team at INRIA École normale supérieure from 2007 to 2010. Francis is primarily interested in machine learning and especially in sparse models, kernel-based learning, large-scale optimization, computer vision, and signal processing. He obtained a starting grant in 2009 and a consolidated grant from the European Research Council in 2016. He received the INRIA Young Researcher Prize in 2012 and the ICML Test of the Time Award in 2014 and 2019, as well as the Lagrange Prize in Continuous Optimization in 2018 and the Jean-Jacques Moreau Prize in 2019. He was elected to the France Academy of Sciences in 2020. In 2015, he was the program co-chair of ICML and the general chair in 2018. He's now the co-editor-in-chief of the Journal of Machine Learning Research. And so with that, I give you the floor to Francis. I will be monitoring chat to see if there are any questions, but people typically jump in and ask questions. So
sure,
try to keep it as interactive as possible.
Okay, please. So thanks, Vijay, for the invitation and for the nice introduction. So today I'm going to talk about joint work with a colleague from INRIA, Alessandro Rudi, and one of our students, Ulysse Marteau-Ferey. And the main topic of the talk will be optimization, okay, but maybe of a different flavor of what you have been used to from our group, which is going to look at global optimization and the non-convex case. So we're going to have a function f that we observe only as some values, and f will have some properties that we will not use a lot, but that we use a lot for the bound, but not use a lot for the algorithm, like some bounded derivatives. But you assume f is define a simple set, and you want to minimize f with the smallest number of function values. So as I've mentioned, there will be no convexity assumption, so you should not expect running times which are non-exponential. Okay, so we look at the class of problems where d, the dimension, will not be 1 million, like we will do in machine learning or optimization. For machine learning, it will be like 10, 20, or 30, 50. And for this type of problem, dimension 10 is already quite big. Reassure you, there will be convexity a lot in this talk, but not on the original problem. So this comes as many applications, like in many places. In industry first, where you want to optimize some process, and computing f is typically complicated. Sometimes computing f requires solving some big model. And this is true as well for machine learning when you want to optimize hyperparameters. Okay, so here the goal will be to how to optimize things globally. All right, so we will have some criterion. So we want to look at to optimize things correctly. So we're going to have epsilon, our precision parameter. Essentially, this will be a precision parameter in function values. You want that your estimate x hat as is close at the function value f of x hat, which is close to the optimal value on omega. And the goal is to have the lowest number of function calls, keeping in mind that we are in a setup where calling the function will be very costly. Okay. Then we're going to look at worst case guarantees. So we're going to want to be doing well on a large set of functions, typically a convex set. And then we take the supremum of the convex set. So it's maximized over like a class of functions. So one interesting aspect of that problem is because we use the uniform, we use worst case guarantees. It turns out that function optimization is as hard as function approximation and uniform function approximation. It seems weird at first because you want to find a minimizer of f, and essentially to get a good minimizer of f, it's as hard as having a good estimate of f for all values. So, and then the algorithm happens to be you approximate f uniformly by f hat, and then you minimize f hat. So if I give you f, only the grid points in f, then you estimate f hat, okay, and you, with any means that you like, using polynomial, using kernel method, using neural networks, whatever you want, and you just need that there is some uniform approximation guarantee. And so your function f hat in blue is sandwiched between the two dotted lines, and then you minimize f hat, and then boom, you get the optimal algorithm. So this is like very nice small book by Novak. And so, so this is, and of course, minimizing f hat may take a lot of time. Okay, so here the goal is accessing the green points will be very expensive, and you're willing to spend a lot of time minimizing f hat. So I've mentioned exponential dependence in dimension, and this is like also well known, that in the number of function evaluations will be exponential in dimension. So if epsilon is a precision, you will need something proportional to epsilon to the minus d. So when d is very large, this will blow up. So this is a classical curse of dimensionality. There is nothing you can really do if you don't make any assumptions. So one way to deal and circumvent a bit the curse of dimensionality is to assume that your functions are a bit nicer than simply Lipschitz continuous. And one way is to assume that you have some bounded derivatives. And then if you do that, the number of function evaluations will not depend as exponentially as before on dimension. And the rate will typically replace the d by d over m. So if m is quite large and m is proportional to d, at least in the exponent, you lose the exponential dependence in dimension. So here, very importantly, the constants will depend exponentially on d. Okay, so you save in precision. So if you want to have low epsilon, then you don't need like to be exponential in epsilon. Voilà, exponential in d with the dependence in epsilon, but the constants will depend on d. And why smoothness can be circumvented? The classical argument is that if a function is 0 at some points and very smooth, it cannot be too large. Okay, so the smoothness will avoid like strong oscillations, and this is an argument where you can go from epsilon minus d to epsilon minus d over m. But as I've mentioned, those algorithms which are optimal in terms of number of function evaluations are exponential time. Okay, and the reason because they approximate using f hat in my previous slide, but minimizing f hat may be very hard, and they're not really concerned about this. So the goal today is to have algorithms which have polynomial time. Of course, when you mention polynomial, you have to be clear in what. It will be polynomial in the number of function evaluations, because I want to achieve the same type of results, having function evaluations that grow like this. The constant may be exponential, of course, but you want at least that once you have n function evaluations, you're safe. You don't have to spend exponential time on top of it. You want to be a polynomial in n, and the idea will be to approximate and optimize as opposed to approximate then optimize. So let's look how we're going to do it. So first, we use a classical reformulation of optimization, okay, as the convex problem. So the goal is to minimize f on omega, and what you will do is replacing this by minimizing a lower bound on f. So I'm going to look at a lower bound c on f. So c is a lower bound if f is above c. So this corresponds to this inequality constraint, and I want to make that black line as high as possible. And this is essentially what this problem is doing. I take the largest lower bound on my problem. So it's convex. Why is it convex? Because there's one variable c. You have a linear objective. Those are convex constraints. Those are linear constraints. So you have a convex problem. So this is one, so if you teach optimization, this is one of many proofs showing that all problems are convex. Of course, the catch here is that the number of inequalities here is infinite, and even more than infinite is dense. Okay, so you have to look with this huge set of inequalities. So the way we're going to deal with it is using ways of representing non-negative functions. Why? Because we have a function defined on omega, and omega here is -1 to the d, so it's like a continuous space. And if we find ways of representing non-negative functions, and which are reasonably efficient, we could like replace this by a good representation of that non-negative function, and we'll be happy. So let's see how we can do it. And the way we're going to do it is by using representations in terms of some feature vector phi of x. Okay, so imagine for simplicity that phi of x is a set of monomials of all monomials of degree r. And if I take a quadratic form in phi of x, then I can express all polynomials of degree 2r. Okay, so it's a classical setup. So I'm going to represent my functions as quadratic forms, okay, in some feature vector. So here phi of x could be polynomials, but given the title of the talk, I will use like phi of x which are a bit bigger, and you will see they will have some better properties. All right, so phi of x here, if you take polynomials, will be quite big because dimension d with degree r, you get like something that will go up, that will grow very quickly with r. And the reason why we use quadratic forms is because we're going to have sufficient conditions for non-negativity will be obtained by assuming that G is a positive semi-definite matrix. So this is, that sign is just definition by definition that G is positive semi-definite. So this means that if this is true, then G of x defined as the quadratic form will always be non-negative. And this is often called sums of squares because if you take the eigenvalue decomposition of G as a sum of lambda I times hi times hi, then you can rewrite this quadratic form using the eigenvectors, and you see that you get a sum of square functions. Okay, so lambda I is non-negative, so you can put it inside the square to get a sum of square functions, hence the denomination sums of squares, which is typically used for those representations. All right, so let's look whether this is efficient or not. And so the question is, we know that those are sufficient conditions, okay, to be non-negative, but is this necessary? Because if it's not necessary, it may not be representing the set of functions correctly. So for polynomials first, because this is how it was done first, the answer is like indeed in dimension 1, all polynomials which are non-negative are sums of squares and vice versa. So there's a nice paper by Rudi. So this does not date back from 2000, but from very old, from the previous century, but there's a nice review paper by Rudi. But this is true for dimension 1, but not from higher dimensions. So let's look at the polynomial case and how they treat this, because our framework is heavily based on what is done for polynomials. So for polynomials, they are replacing these non-negative constraints that we use to show that C is a lower bound by simply saying that f of x minus c is a sum of squares. Okay, so it's a sum of squares, so it's c plus that sum of squares, that phi of x are monomials. So because monomials are finite dimensionals, if I call f, if I represent f my polynomial as the same basis, okay, then if I assume for simplicity that the constant u is inside my space, then what I have here is a finite dimensional constraint. F is finite dimensional, C as well, okay, of course, dimension 1, and A as well. So here, this I can solve. I can minimize C such that F is equal to this, with A being PSD. So this is the area of sum of squares optimization. Okay, so started by Jean-Bernard Lasserre and Pablo Parrillo 20 years ago. And this is a problem we're going to solve. So this is a finite dimensional semi-definite problem because everything is finite dimensions here. And if for the optimal value of C, which if for the minimizer of f star, f minus f star is a sum of squares, you get exactly the solution. Unfortunately, as I've mentioned earlier, not all polynomials which are non-negative are sums of squares. And that's why otherwise they need to use things which are a bit more difficult. They have to use a so-called localization set, typically an L2 ball, and you can show that if a polynomial is non-negative on this set, if only if you can write it as a sum of two polynomials, Q, which is non-negative, this, which is non-negative as well on the constraint set, and P, which is non-negative. So you can check that if Q and P are non-negative, then f of x is non-negative on the constraint set, by definition of the constraint set over there. What is kind of amazing, and the proof is it's not trivial at all, is that those two polynomials, which are non-negative, can in fact also be chosen as sums of squares. So they can be represented as phi of x times a phi of x for some non-negative a. The catch here is that the degree of a is not bounded. So in this presentation, there is no need to take a being of higher degree as f, because of this constraint, all those higher order monomials will be 0. So you don't need here to have like higher degrees, but here it turns out that this result is true if only if P and Q may have increasing degrees. Okay, and this is why you need so-called hierarchies of problems of increasing degree. So you don't only use the degree of f, you have to go higher. And this is a hierarchical thing, which I've seen a lot of applications since the seminal work of Lasser and Pai.
So Francis, there was a question in the chat.
Of course.
How do you ensure that the dual problem is tight? I guess that was.
You mean but that's okay. So here I am assuming that you can solve SDPs exactly. Okay, so but if you solve them up to epsilon, then you get a solution up to epsilon. So I don't know if this is what is meant. Yeah. All right. So here the goal will be to move away from polynomials, which have this like issue that not all that all non-negative functions are sums of squares. So we move to a different phi, and phi will be infinite dimensional. So we will lose apparently because we have infinite dimensions. So we have to deal with large things, but we're going to have this possibility of representing all non-negative functions as sum of squares. So let's see how it works. So we're going to use kernels. Okay, so what is a kernel? This is a kernel space is a space of functions, a Hilbert space of functions, for which you can represent function evaluations as a linear form. Okay, so g of x will be a linear form. So by the Riesz representation theorem, there has to be some phi of x, so that g of x is a dot product between g and phi of x. Okay, so you can say L2 is not an RKHS because the Dirac is not a function. Okay, but if you restrict the set of functions, then function evaluation becomes bounded. And for those spaces, the key quantity is the so-called kernel, which is just a dot product between phi of x and phi of x prime. Okay, so this is the what you need. And it turns out that if you know how to compute the kernel, you don't need to know phi of x explicitly. You know it exists, but you never need to know it explicitly. So all algorithms dealing with those spaces happen to be in infinite dimension, but in fact only using finite dimensional representations. And I will show that in a moment for this problem as well. So examples, classical, all the sub-OLEV spaces, so all the spaces with like square integrable derivatives are RKHS if the order of differentiation is large enough. Okay, so we need to have, as D is increasing, to have more and more differentiable problems. So this is a classical area of kernel methods. And the classical kernel that you probably have seen before is that if you take the exponential kernel, so exponential of minus the Euclidean norm between x and y, so no square here. If you had square here, that would be the Gaussian kernel. That would be even with smoother functions, but without the square, you get a space of function with that order of differentiation. All right. So the key thing and why people like kernel methods so much is that if you have any problems where you want to optimize over a function g in the RKHS, where G is only accessed through its functional values at some points. Okay, so typically this is for machine learning, you're going to do like regression. So you observe the function G with some noise at some points xi by x1, x2, xn. You minimize the loss, which is typically the average over your training data. That loss depends only on function evaluations. So if you only have this, plus you add the penalty of the RKHS norm, you want the derivatives to be not too big, then you know in advance that you don't need to look for a function G in a very big space. You can restrict to a finite dimensional vector space spanned by the kernel functions like that. Okay, so instead of looking as G, which is in the Hilbert space, infinite dimension, you look at alpha, which is a vector of size n. Okay, so this led to all the kernel things like in the last like 30 years. And from that, you can express G of xj only through the kernel functions, and as well you can express G squared, the norm of G squared only with kernel functions. Okay, so this is what we use typically in kernel methods, and we will see that this will be extended to the quadratic form as well. So here, this is working with the linear forms in the feature vector. We will extend it to the quadratic form case. All right, so let's first look at what we can do if we go infinite dimensional. So we're going to reuse the exact same optimization problem that we had for polynomials, but we replace phi of x by from monomials to from the feature vector associated with an RKHS. Okay, so typically we take a subordinate space for simplicity, and this corresponds to what I've described earlier. Okay, so we have this phi of x that we know is infinite dimensional, and the first key result is that we know that, of course, under some conditions, that non-negative functions will be represented as sum of squares. Okay, so this is a precise work. So this is joint work with Rudi and Ulysse Marteau-Ferey. Is that if f as is minimized as a minimizer at the interior point in omega, and the value is f star, and if f is sufficiently differentiable, then we know there exists some S star, so that f minus f star can be represented as a sum of squares. And even better, it's not written there, but S star can have rank D. So we know that we can have a sum of D squares. Okay? So this is showing that if I can solve that problem, I'm going to solve exactly my original problem. Okay, so the fact of replacing the non-negative constraint by the sum of squares will not be a problem. But of course, I still have like two major issues, is that A here is now an operator, okay, in the infinite dimensions, and plus I still have a dense set of inequalities. Okay, so let's look at how we can avoid those two problems. So the first way will be to replace this dense set of inequalities by a subsampled set of inequalities. So we're going to only take n points, x1 to xn, typically random in omega, and we're going to replace the equality constraint satisfied for all x by an inequality constraint satisfied only on those n points. Okay, so now I get finitely many constraints. Okay, the question is, will it work? So it will work if we add some penalty, very much similar to what we do in machine learning. We're going to penalize by the trace of a, or is it you can replace any spectral function would work as well. And this was done for polynomials by Löfberg and Parello, and we extend this type of approach to the infinite dimensional case. But what is hard in the infinite dimensional case is that this problem is not equivalent to the original problem because you have fewer inequalities. But what we show is that we have approximation guarantees related to the task of optimizing f. So remember from the first slide or second slide that we know that if we want to optimize f, we need to access a certain number of function evaluations. Okay, we need to know the value of f at certain points, and the optimal value was of that form. Okay, so here there is a d over 2 because we replace bounded derivatives by derivative in L2. Okay, so it's a minor thing, but the key is that if you get more derivative, then we know exactly how many function evaluations we need. And it turns out that we could show that If you solve that problem, you get a similar type of guarantees which are a bit weakened. Okay, we know that we have the factor of 3, which is not optimal. And so this is showing that if you can solve that, then you achieve like up to one constant here, the optimal rate of global optimization. So again, here there is like a constant that depends exponentially in dimension, okay, like before. But the goal is to have to be exact or close to exact in terms of exponent. Right. So now we know. And why is it okay? Yep. Go ahead.
Question. So when you say you evaluate the function, you're getting it precisely. There is no error in the evaluation.
Good point. At that moment, no. At that moment, we need to know f perfectly. We have not considered the noise issue. What you could do is to replace this equality constraint by the difference, by the L2 norm of the difference, okay, of those two vectors, so that will deal with noisy evaluations. We have not done it. Okay, we have not studied it, but that's because the task of zeroth order optimization is a bit more complicated. So I think that's a good question, a good extension, but we have not considered it. I don't know how you would do it. We have not considered it. We have not tried it at all. One thing that you may wonder is, if I can subsample the equality constraints, why can't I simply subsample the inequality constraints that I started from? Okay, why can't I simply replace this by simply that? Okay, if you do this, what you're doing, you're essentially taking C as a minimal value of all the f of xi's. So you just do random sampling. I sample xi's randomly. I compute f at those random values, and then I take the minimal one. Okay, so random sampling is not that stupid. Why? Because it's optimal if m is 1. So over Lipschitz continuous function, you cannot beat random sampling. Okay, of course, if you know more, you can do better. Huh? But at least, so random sampling will be optimal only for when you have no smoothness. And why cannot it be used when you have smoothness? So because if you subsample an inequality like that, so this will be a very hand-wavy argument. Take on the right a function for which is like positive at all the black points. One of them is a quadratic function here. Okay, so if the spacing here is epsilon, then here you will have epsilon square. Okay, and so then this means that you will never be able to get this quantity less than epsilon square. Whereas if you impose the function to be 0 at all of those points, okay, then with smoothness, you will be able to reduce those oscillations. On the right here, the quadratic function is infinitely smooth. Okay, so and epsilon square cannot be beaten. Here, you can beat it, and this is so this is classical in the context of approximation theory. If a function is smooth and 0 at many places, it cannot be too big. If the function is positive at many places, it can be very large, or it can be like even the negative part can be very large. So of course, this is like hand waving, but this is how the argument works. All right, so now this is still infinite dimensional of A. Now let's see how we can optimize, and this is where things are. We can leverage earlier work that we had with both still Ulysse, Marteau-Ferey, and Alessandro Rudi, is that we have a form of representative theorem. If you minimize a function, an operator A, you want to minimize with respect to an operator A, which you access only through quadratic forms, okay? And if you penalize the trace of A of any spectral norm, then even before you start the algorithm, you know you can look for A in a finite dimensional space, which is essentially spanned by rank 1 matrices. So we know that we need to take C being a PSD matrix, but only a matrix of size n, and not an operator in infinite dimensions. And once you have that, it's done because you have A in a finite dimensional space. You can take A times this. You can check that it only relies on the kernel matrix, and you can optimize. And this is this leads to a semi-definite programming problem whose complexity officially, with the entire point method is n to the 3.5. So this is like polynomial time in n. But in the paper, we have we tried a more efficient Newton algorithm, which is only O of n. Right, so as a summary, what is a final algorithm? Give me the function f, give me your set omega, hypercube if you want, give me some parameters lambda, and then a sample points uniformly, or either randomly or quasi-randomly. Then I compute my kernel matrix. Okay, so you can take K being the associated Sobolev kernel. So this is typically like simple functions, like the exponential kernel. Then you compute a bit of square roots to compute like an approximate function of to compute phi j. You compute here function values. Okay, so this may be costly, and then you solve this semi-definite program. Okay, which is like finite dimensional. You obtain Lagrange multipliers for those like inequalities, and boom, you output the value C, and you output the estimate x hat based on the Lagrange multipliers. So what I've shown earlier is that if n is large enough, okay, then the value C will be approaching the optimal value, the minimizer of f, with a given if n is large enough. And similarly, you can show that x hat will approach the optimal value if n is large enough. So small, like very illustration in dimension small. Okay, so it's a function in 2D. Okay, like this with like few local minima, a global minimum, and it's mostly for illustration purposes. So here we sample the purple point. So this is quasi-random. So we access the function only at those like purple point. The model, the algorithm, we essentially model the function and optimize the model essentially. So this is the model that we obtain. And in the blue, in the red here, this is the trajectory of the Newton algorithm. So it moves from the center and ends up in the global optima. So here on the right, this is to highlight the fact that there are many other algorithms that are working well on that problem. And one good algorithm, if you're quite smooth, is to use gradient descent with random restarts. Okay, so this is here. I have adjusted the number of random restarts to match the total number of function evaluations, assuming that accessing a gradient is as costly as d function evaluations. And you can see here, it corresponds to 5 restarts, and one of them is doing correctly. Okay, so this is just to highlight the fact that there are many algorithms to do that. But if you add some high frequency, component of the function, okay, so I don't know if you can see on the slides, but this is adding a high frequency. We are not perturbed so much, we still optimize correctly, whereas the gradient, because of the high frequency, is totally noisy, and you get something which is not working, you get stuck. Okay, so just to highlight the fact that algorithms that do not rely on gradient are more robust to perturbations. So this is in 2D. We can do this in like 8 dimensions. Okay, so we took like a similar functions, and we run either random search, okay, or we do, which is in blue, random plus gradient descent, okay, and our new method like globT kernel, which is named after globT poly, which is the package for doing polynomials. And you see that when the number of n of function evaluation is increasing, we get like something that goes down, whereas the other will go down as well, but in a much slower way. It's just to highlight the fact that the modeling on top of random sampling will make it convert fast. So clearly here, I'll come back to that later, but we don't have something yet that will work on high dimensions, because n here, it's hard to go beyond like 1000, but this is future work to make this quick. But that I want to emphasize that is much more general than optimization. So this is let's look at duality first. Okay, what we learn in the.
Just before there was a question in the chat.
Okay.
So can we optimize the hyperparameters, the kernel bandwidth, or is it assumed that?
I think this is for us very easy. Why? Because we can do cross validation. But here, you can validate by trying several values of lambda and the bandwidth parameter, and then take the output, compute f at that output, and boom, you take the one with the smallest f. So in machine learning, you need to estimate test error to do cross-validation. Here, because the goal is to do optimization of a function f, you just compute f and say the best one. So in fact, this is easy, and this does not cost too much in terms of function evaluations. Question 1. Question 2, how difficult would it be to add constraints to the method? I'll come back to that in a moment. So let's look at duality, because we learned in all good optimization classes that duality is important. So let's do like some duality. So this is my problem. So I'm going to add, it is a constraint problem. So I'm going to add a Lagrange multiplier here for the constraint problem. I will call it mu of x. Mu of x will be non-negative because I have an inequality constraint. Then if I add mu of x and add it back to the objective, you do like a few lines of computation, and you end up that the dual problem is a problem on non-negative functions again with an equality constraint. This comes from optimizing over C. And then you end up with the objective, which is the integral of mu times f. So what do you get? You optimize over probability measures the integral of f. Okay, so this is a very classical reformulation of optimization. So the optimal mu will be a Dirac, or will represent the Dirac around the global optimum. Okay, so this is not a Dirac, but we have a Dirac there. So you can see here that the dual is also a well-known problem. Then you can see what's happening if I replace this by my sum of squares. Okay, so that if I replace this by my sum of squares, I also get some Lagrange multiplier mu of x, not anymore constrained to be non-negative because I went from inequality to equality. And then the PSD constraint, when I optimize over A, I get a PSD constraint on the second order moment. So I see mu as a sign measure that is summing to 1. Mu may not need to be non-negative, but the moment has to be PSD. And this is the dual problem. So why do I show it? Because first, this extends earlier results on polynomial by Jean-Bernard Lasserre. But why I'm showing it? Because here, if you start from the original problem, primal and dual have the exact same property of being represented on non-negative functions. So whenever you see something like that, you could decide, oh, I'm going to represent that one or that one using sum of squares. And I could choose the two of them. So which one you should choose? First, when we try to work on that, we first chose that one. It was the incorrect one. So why was it the incorrect one? Because you want to leverage smoothness. Okay, so you want to make sure that at the optimum, your non-negative function is a smooth function. Here, this is true if f is sufficiently differentiable. But on this one, the optimal mu is a Dirac, so super non-smooth. So if you try to replace negativity by a sum of squares, you have to do it in the correct primal or dual. So some problems are naturally given through the correct format, but some problems are not, and I will show examples. So the extension I'm going to consider is all problems which are minimizing some function with some non-negative constraints. And what you can always do is that to replace this non-negative constraint by a sum of squares, you have to penalize and use subsampling, and boom, you get an algorithm to minimize this. Okay. Of course, you can choose primal or dual, and so this works for any problem. Of course, you need G to be like a linear function in theta. Okay, otherwise, kind of you don't get a convex problem. But most problems many problems are obtained that way, and we show two examples. One will be optimal transport, and one will be optimal control. So let's look at that. So the optimal transport, this is a joint work between Adrien Vacher, Boris Muzelek, Ale Rudi, myself, and François-Xavier Viala. So we look at optimal transport. So here, for the next 2 slides, either you know about optimal transport, and this will make sense. Either you don't, that will not make sense. Just I will not spend too much time on defining optimal transport. So that would take me like a full lecture. So what is optimal transport? You have the classical primal formulation is you want to, given 2 measures, okay, you want mu and nu, probability measures. You want to find a coupling between those two measures that is minimizing some cost. Okay, it's often called when the cost is the norm, it's often called the Wasserstein distance. So this is used in many areas of in probability, machine learning, statistics. And so here there's a dual problem called the counter-average dual, which has a sum form. You minimize over functions, and those functions are coupled with with a constraint like that. That the cost has to be bigger than u plus v. U and v are typically called the counter-average potentials. And what has been shown before, very much in the same way as optimization will benefit from smoothness. If you want to estimate optimal transport from samples, you can also benefit from smoothness. There is a curse of dimensionality for estimating optimal transport that you need, like the rate of convergence when n grows will converge to 0, but very, very slowly in D. If you assume that your densities are smooth, you can get like a nice, better behavior. But the problem that what Rudi and Berthe had is no way to get like a polynomial algorithm in n. Essentially, so here you should see me coming. I'm going to replace that constraint by a sum of square constraint. Okay, I'm going to take that c is u plus v plus the sum of squares. So here there are additional issues that u and v have to optimize over u and v, which are functions. But I can use kernel methods. And then I'm representing u as a function in a kernel space, same thing for v. I subsample like I did before, and very similar to optimization, we obtain the exact same rates of convergence for the value, but now we can do this in polynomial time in n. This is for optimal transport. Let's look at optimal control. Okay, so if you have never seen optimal control, this will look very weird. If you know about reinforcement learning, we can solve the LP formulation of reinforcement learning. And we have done this with other colleagues, Héloïse Berthier, Justin Carpentier, and Ale. So this is the standard optimal control problem, where I have some dynamical system, which is controlled by some control U. And I want to optimize some cost function over U, which is the average of some loss function L and some final cost. So this is a classical optimal control problem. The goal is to compute the so-called like optimal cost to go V star. And it's known that there is a dual to that problem, which happens to be like a partial differential equation called the Hamilton-Jacobi-Bellman equation, and which ends up can be solved by some big optimization problem, which is suprema over something plus a big inequality constraint. Okay, so essentially, what people have done for polynomials is to replace this by sum of squares of polynomials. You can replace by sum of squares of with kernels. Okay, so the added benefit here is that you can use modeling a bit. So the good thing with kernel method that there's been 20 years of research on how to do modeling with them, and you can use this within those tasks. All right, let me conclude. Oh, further extension for the question. If you want to do constraint, okay, then it's possible. So if you want to minimize f with a constraint g is positive, then you can have a sum of square representation, which used a lot in polynomials, which is used a lot with polynomials, but you can use it as well. Is you want to represent f as c plus one sum of squares plus g times one sum of squares. You can check that if g is positive, this is positive, and it turns out that, and this is work that we're currently like finishing, this provides a reformulation for constraint problem. You have not tried it, okay? So, okay, to conclude, I've presented like a method to do global optimization through kernel approximations, and the idea was to do jointly approximation from a finite sample and optimization. This was done using sums of squares representation, but the key addition is to go infinite dimensional. So this creates benefits, like all non-negative functions are sums of squares, of course with technical assumptions, but this is a benefit, but there is a drawback of requiring to do subsampling, but this can be done in a controlled way. Then, so further extensions. So of course here, we are not ready yet to go live and optimize like problems with n being like super large. Okay, so we need n to be very large, so n the number of functional evaluations where the dimension will grow. Okay, so you can't avoid totally the curse of dimensionality. So when d grows, you have to let n grow. N cube is not acceptable, but we already have some ways of going below n. One thing that we're also looking at is looking at adaptive choices of sampling points, very much like Bayesian optimization. A key problem is that at the moment we don't have certificate of optimality. So I can only tell you that if n is big enough, we're going to achieve the minimal value of f, but I cannot certify a posteriori if this is working. This is very important in practice. And finally, there are other problems you can look at when you have some such infinite dimensional like convex problems. And if you want to know more, we have an archive submission plus a blog post on it. And on this, I will thank you for your attention and take questions.
Thank you, Francis. I was going to ask you the question about adaptive choice of points and comparison to Bayesian optimizations, but you already touched on it.
Okay, so the comparison, okay, so that's a good point. So what is Bayesian optimization doing? So Bayesian optimization is two things. Is given a set of points, okay, you do a Gaussian process to model the function, and then you minimize essentially the model. So this, the modeling part is exactly the exact same thing as here. Okay, so you're going to model the function and minimize the function. Okay, what it adds on top of it is an adaptive selection of points. Okay, you're going to select points one after the other, and they're using some probabilistic techniques to get some like confidence bound, and then you minimize the confidence bound to select the extra point. Okay, so they are going to be adaptive, so they may work better in practice, but there's a huge caveat that in the worst case sense, and again, this is in the worst case sense, adaptive optimization does not bring you much. Okay, so this is in the worst case sense. So it means that there's hard problems for which this will not buy you much. In practice, it often buys you a bit, okay, to do adaptive selection. But Bayesian optimization is one subcase of that. And this is why we want to do adaptive as well, is to be able to sample more in location that matters. We are not there yet.
Thank you. Are there any other questions from the audience? So it's open to questions, please.
Very nice presentation. Your numerical results, you mentioned a Newton algorithm. I kind of missed that. Could you say just a little bit more about what's the Newton algorithm doing there, if I heard you correctly?
Yeah, so this is, let's take that problem. So we need to solve that problem, okay? And so this is an SDP, okay? And so what we do is we take the dual, so we put a Lagrange multiplier here, and we solve the dual using Newton method.
I see.
So why we do that? Because there's a very nice, so we use, to be perfectly like precise, we use like the damped Newton algorithm, which is used by Nemirovsky and colleagues. And why we do so is because with that technique, you can solve an SDP without ever computing a single eigenvalue. Okay, so it's an algorithm that will remain in the feasible set without checking it. And so this is very advantageous to solve the SDP without eigenvalues. That's why we do that's why we use the Newton technique, but it's still n cube. And so to go below n cube, we have to resort to like replace these equality constraints by approximate equality, use techniques from Kernel methods. So the good thing is that since we rely on Kernel methods, we can leverage like 20 years of research aiming at making Kernel methods go from n cubed to O of n. And this is what we have done it already. It's to use like what is called Nystrom approximation, where you can avoid n cube and go to n times a constant. Of course, the constant may grow, but at least you can run it on bigger things.
Thank you.
A few questions on chat. I don't know.
And we have a compact Kernel manifold. In fact, so you have two, and you have, I would say you have two answers to that. So if you have simple compact manifolds, okay, like the set of orthogonal matrices, yeah, sure, I think that would work reasonably the same. But what we are about to publish or going to release is if you have a manifold defined by functions, okay, like a function equal to 0, then this would work as well. Okay, so this is one version. So this is yeah, so everything was pretty much the same, but of course there are some constraint qualification issues which I forgot, but this you can deal with it. It depends if you want. It depends if you want to do something which is just for running the algorithm or proving that there exists a sum of square representation. So those two are a bit of a different nature.
There's another question on how do you know that the sampling is sufficient?
That's we don't. This is the issue. So this is why we want to get certificates of optimality. Okay, so this is like, so I've talked to I presented this to like optimizers like Jean-Bernard Lasserre and colleagues, and always the same question: we want certificates. Why? Because with polynomials you get a lower bound using certificates, okay, and then upper bound by having like candidates for X, okay, and once they match, you stop. But for us, we only know that we can improve going down, but we never know where to stop. So once we have those certificates of optimality and we are getting close, then we can know where to stop. But that's a key. That's a big missing part at the moment.
I have a question, I guess, along those lines. Are there ways to to sample so that you can check that some of your assumptions are satisfied?
I think one hope that we have is that by sampling points, if your function happens to be not super differentiable, then the rates will be not as good. But you would expect that if you sample more points around the non-differentiability points, then you should compensate for that lack of differentiability. This is our goal, okay, that we want, I think our goal with being adaptive is that we hope that we're going to very much like Bayesian optimization, we're going to improve the certificate of optimality by sampling good points. So at the moment, we do have certificates from the bounds, but they are very, very, very non-tight. So the certificate will say that the function value is bigger than something like absurdly small. Okay, so but the one hope is that by you would sample points not only to get the better candidate, but to get the better certificate. So at the end, you have two goals, and I think for me the bigger, the most important part would be to get to improve the certificate. And this is classical in optimization. Often when you have primal dual algorithm, often one of them is already solved and you spend all of your time finding certificates. And so here we're a bit in that situation.
Got it. So then when you talk about adaptive choice of sampling points, is one way that you would do it is to have some points and solve the problem and then identify regions where you need to focus.
This
more,
is one way, but that would be too costly. And
okay.
so we have other ways, a bit similar. No, we have, for doing this, we need to access F. Okay, so if your goal is to have a minimal access to F, you cannot do that. But in some situations when the F is not too costly, you could do it. But no, I think here we rely, in fact, those like to obtain those results, which is based on that argument that if a function is 0 at some points, it's not too big, then you can choose the points adaptively, okay, in a better way. So this is more what we are, this is more along those lines that we are trying to do non-adaptive sampling. But this is very similar to Bayesian optimization. And if you look in that literature, you have like a mean plus variance, and this is very similar to what we're doing.
Got it. But just to clarify too, already you're accessing F n times, right? So it seems like a natural way to get something better would be to use half of those n first and then another half of the.
In fact, you can by doing that, if you you can in fact improve the dependence in epsilon by doing this, by using like doubling trick. You could get a log of 1 over epsilon, but the constant will still be exponential.
Got it.
But clearly, also there are a huge bag of tricks. Okay, so if you take like those clearly here, you notice that maybe those points are not so useful, so you should focus optimization on those ones and solve the SCP only on 8 points. This will work much better as well. So, but here the point is that if you don't want to get any certificates, you can play a lot of tricks. Okay, so the goal is the final goal for us, and this is the goal, the same goal as sum of square optimization with polynomials, is to get certificates. Because if you get certificates, then you can spend some time, then you stop, and the user will be satisfied because he or she will know that it's done. Okay, and that this is a goal, and this is, I think, it's only going to be really useful, in particular compared to randomized random descent, if you can provide certificates. Okay, so this is why we're working a lot on that at the moment.
Thank you.
Slightly different question was, I mean, so smoothness here is used for the representation by the recursive kernel Hilbert space. Is there a way to use the derivatives and things if you could evaluate those? Or?
Oh, I think somebody asked me the question once, and I think sure, because in fact, if you know more, you model better. I don't know how you would fit it with the non-negativity constraint. This unclear how you would leverage it because now I don't. In fact, I don't know. In fact, I don't know how you would. What is known is that if you observe derivatives, you still have that part of the problem with if you subsampling, that part which can be solved in polynomial time is preserved if you observe some derivatives. But I don't know how you would use derivative in the sum of squares. That's I don't know. That's a good yeah, good question. I wouldn't know.
Thank you.
Well, Francis,
Any
I have a
more
question.
Go ahead.
Yeah, I'm just wondering if if you've thought about how this approach might generalize to the multi-objective problem. So if you're looking for the Pareto frontier of non-dominated solutions, that's under some conditions a smooth function, and so could this be applied to effectively sample the Pareto frontier and then reconstruct using your kernel optimization idea the rest of the frontier so that you could basically then interpolate and perform Pareto optimization this way?
Okay, so if one obvious answer is that if you have f and g, f is c plus sum of square, g is d plus sum of squares, and then you want to have c and d being small, large simultaneously. Oh, right. I don't know, because you minimize lower bounds. I don't have an answer like right now, but I do think it's possible because it's because of Pareto. I think it depends. If you have a convex Pareto frontier, yes.
Yeah, if it's convex, yes, right.
If it's not convex, what I described works for the convex case.
Yeah.
If you're not convex, and this is what you want to do because this is what you want.
That's why you want a Pareto front, not the convex hull, right? Yeah.
I don't know, but that's a very good point. I don't know, but you could imagine certain tricks. But I think the convex reformulation is not true from the start. So that one,
right? Convex combination doesn't work for that. Yeah.
I think that thing failed from the start, and so you would need something different. In fact, the proof of duality relies on, I don't know. That's a good question. I wouldn't know. That's
yeah. Well, we're thinking about. Yeah.
Okay.
Enjoyed your talk. Yeah.
Okay. Thanks, Alfred. Thanks, Al.
Yeah, thanks.
Any more questions or? If not, let's thank Francis for an excellent talk. Thank you very much for the seminar. Everyone enjoyed it. I'm going to end the video now. Thanks. Bye.
I think I'm supposed to meet a few people like in the gather town. So should
Yes, yeah. Right.
No, so thanks Vijay for hosting me and
Right.
enjoy your day. So I'm going to move into the gather thing, or we can stay here. I don't care.
If you want to, then if you guys want to meet here, then I can maybe make a whole. Let me first stop the recording.